It is widely known that malaria is one of the world's deadliest diseases, but what makes it extra dangerous is that 90% of cases are asymptomatic, or symptom-free. These people act as silent spreaders. Mosquitoes who bite them can spread the malaria parasite to others who may develop symptoms and potentially even die. Therefore, in order to eliminate malaria from a community, we must test everyone periodically. And in developing countries where malaria is most prevalent, this means that tests need to be very cheap, 20 cents at most.
Lateral flow assay tests are widely used to test for malaria. They meet the price criteria. It costs about 12 to 20 cents per test, and they are also very easy to use, which makes them accessible. Pregnancy tests and COVID tests are both examples of lateral flow assays. Lateral flow tests detect the presence of antigens, or markers of the disease. The antigens found in the collected sample bind to antibodies with chemical labels on the conjugate strip. As they flow down the paper, they encounter two more lines of antibodies. The test line binds to antibodies with the antigens, and the control strip binds to all other antibodies. The greater the concentration of labels on each strip, the darker the line. This explains why we see two visible lines on a positive test and only one on a negative test. As you can see, the concentration of antigens might really influence the accuracy of the test. The more antigens there are, the easier it is for them to bind to the antibodies and show up on the test. Less antigens can cause inaccuracy. Too much sample can also overwhelm the test. The thing is that malaria tests used to be very inaccurate. In 2011, only 15 of 54 brands could test with 90% accuracy or higher. It was clear an improvement was needed. However, instead of improving the actual tests, David Wright, a chemist at Vanderbilt University, developed a device that improved the concentration of any sample. His device, using a process known as nickel chelation, improved the sensitivity of various tests by 16 to 20 times. There were two steps to this process, which happens before the test. One, to use nickel beads to selectively bind to the amino acid histidine, which malaria antigens have a lot of, and two, use magnets to cause the metal beads with the antigens to transfer to the test. This process could concentrate the amount of antigens in 10 drops of blood to the volume of just 1 drop.
This technology was revolutionary, but in a way that you might not expect. The way Wright's team prioritized low cost, familiarity, and overcame language barriers, the experience was essentially the same, just with a few extra steps, proves that it's critical to think of not only the scientific process, but the people who will be carrying it out. This device would be of little to no use if it was expensive, complicated, or came with long instructions that were difficult to translate. It proves science is not only about molecules and cells, it's a part of society functioning as a whole.